process models. He's a professor for business informatics at the Universität des Saarlandes in Saarbrücken, and he's also a senior researcher, research group leader, and many other things since I think 2006 at the DFKI in also Saarbrücken. He has studied in Münster. I think that he was too late to get into my introductory course there at that time. I think he was too advanced for that. Then he did his PhD in Mainz, and now since 2006 he's at the DFK. It's your turn.
Thank you very much for the nice introduction here. Yes, ladies and gentlemen, it's really a pleasure for me to be here today. Actually, it's the third time I've been here in Kreta. It's very nice that I was invited once again. Last week I already showed some slides to my wife, and she promised after some slides I might be not invited next year. So I'm really looking forward for that, but we will see. Also the work I represent here is in very intensive cooperation with Wolfgang Leisig, so it's a little bit more practical oriented now, but I will show you some interesting possibilities to use composition calculus in the field of large process models. I'd like to start with my talk in a small nutshell. I think all you know are large language models. Here it's one module with a left and a right interface. In the left interface you have some input text, and the idea of a large language model is to produce some output text. And the main idea of my talk, the main idea I like to present to you today is that you do not put some text into the large language model, but you put some process into the large language model. And then the result of a large language model is not some text, but some process. This is the main idea, and I like to elaborate now on that main idea. And actually, that's my talk. So I'm almost finished now, but now I will go into some more details. Actually, my talk is structured in 3 parts. In the first part, I will talk a little bit about large language models. And in the second part, I will talk about some process models. And I think in particular in this part, I will give you some answers to the questions to Wolfgang to the first part regarding the question what might be inside the different modules. And in the last part, I really come then to the large process models. So, the most abstract view, I already showed you that slide. Let me give you some more details on this. I think one of the most prominent applications are large language models is the style of ChatGPT. You have a dialogue system, you have some kind of prompt, then you have an answer, then you might feed into the large language model in the form of a dialogue system with find prompt, and again as an answer. I think this is a really prominent application of that. And of course, I think nowadays there are many more applications. I give you an overview of some more. For example, translation. We have some input text, and the large language model generates some translated text. And there are some really good companies who provide such translation services, and it's really useful in everyday life. Another example for large language models is a form of closed text. Some of you might know from some exams or from school, you have a closed text, and the closed text language model has to complete the text. And if you look at benchmarks for this, the benchmark really shows really good results for such kinds of very particular tasks you might give to a large language. Of course, there are many, many more application cases. I don't want to go into details, but I'd just like to give you an overview how different, very particular cases can be used for this kind of technology. If you look at a little bit more on a technical level, how a language model works, then it is more or less a kind of a token predictor. You have on the left-hand interface, you have some tokens, token 1 to token n, and the large language model tries to predict the next token. Actually, this is the theoretical foundation, how the language model works. And in every application domain, it's always the same. You have the input. The input is transferred to some kind of tokens. Then the token predictor tries to predict the next token. And actually, that is technology. Concrete algorithms, methods to really build this black box are very complicated. There are many different methods and techniques how to do this. But in general, it's always this method. What is also a very interesting question in this context, what is really a token? Sometimes, in some models, a token is a simple character. So you have just some characters which are feed into the large language models. Sometimes a token is a word. Sometimes you use some n-grams, 2 grams, 3 grams, 4 grams as possible tokens of the large language models. Sometimes part of words, and what becomes quite famous with ChatGPT is the so-called byte pair encoding, where you try to identify the most common sequences of typical characters, and these are the idea for using this. What is also interesting, but that large language models are not only used in the textual domains, there are very famous and very prominent domains in which large language models are totally differently used. And I think one really interesting application domain is the prediction of protein structures. There was a very famous article in Nature 2021. Also, this method of protein prediction becomes the method of the year in 2021. And a couple of weeks ago, in June, I think two weeks ago, there was the third edition in AlphaFold 3, which has a really deep impact on medicine and biomedicine and things like that. So in these domains, large language models are today also very intensive in use, and they are quite revolutionary in that domain. But also in this domain, it's the same game. You try to identify different tokens, and I looked it up in the paper in Nature. In this system, AlphaFold, they used about 25 different tokens for the different amino acids, some unknown type acid, a gap token, and a mask token. And this is the main idea how the large language model is used in this domain.
Peter, can you say something about the N? I mean, you have tokens from 1 to N. What is the N for that example?
I'm not pretty sure, but I remember 64 or 128. So it's typically an exponential function for this application domain, but I'm not really an expert of that. I was just looking up the tokens for this application domain to really understand how the language is used. But if you're interested to look at the detail there, I think there's an appendix about 60 pages. So there are very many details out here.
I'm actually interested whether you're claiming that there's always an N is correct.
I don't think so. That is the claim of the corpus. So large language models are not only used for text domains, but also, as I showed you the example from the nature sciences. And I think all of you know applications in the context of program code, modeling pilots, programming co-pilots, or the application domain of visual chunks and visual computing, I think. And there, the tokens are really identified on pictures and frames. And this brings me to the question, what is a token in the case of processes? What is really a token in this application domain? And I try to give you some ideas how a token can be defined in this application domain I'm very well familiar with. So, process models. What is a process model? I think a very typical characteristic of a process model are several steps in the process, and here's a very tiny example. First step, it's again a step module of a process. On the left-hand side, there's ready to bake. It's a starting stage, starting condition. Then there's just one action, the bake transition, and after the bake transition, you have some some bread on the counter. So it's a really, really simple step. And in this example, you have the second step. The second step tries to move the bread from the counter to the shop. The third step is the move to shop step in the process. And also in this example, you have a fourth process step. And as you might remember, you always have the different step modules with the left interface and the right interface. And these four different process steps, you might already think about it. These four different process steps can be composed based on the composition calculus. And now you have the process on the bottom. It goes from the bake step over the supply trade step, then to the move to shop step, and to the sales step. And here you have the case that the left interface of this module, ready to bake, age free and shelf empty, is the same as the right interface, ready to bake, age free and shelf empty. So here you have some cyclic structure, but as you might already identify, you can write up this, run this process with the composition calculus, bake, composed with supply trade, composed with move to shop, composed with sales. What is now very interesting, if you have another bake step, here in the middle, you have another bake step. And the interesting thing is now that this bake step provides an extension. And what we typically know from processes, you have some kind of concurrency. It is pretty clear from this graph that the second bake step comes after the supply trade step, because here's an arrow. But if the second bake step is before, at the same time, or after the move to shop step, is open. So you can generate some kind of concurrent behavior, although you are just composing different process steps in sequence. This is a very interesting phenomenon. So this little example shows that you can compose processes which have some kind of concurrency. What is now interesting, you can do it one step further, a single bakery run. Then you can define one-step bakery run just as a bakery run, a second bakery run as a one bakery run composed with a bakery run. A three-step bakery run is a two-step bakery run composed with a bakery run. And you already might recognize is you can use some kind of iteration recursion. So an n+1 bakery run is defined as an n-run bakery run composed with a bakery run. And now this is an infinite process, and of course this is really large. What is even larger than an infinite process? This is already a large process model. Of course you might now say, oh, this is a very simple large process model. It's not very, very realistic. I'm pretty sure that you're thinking about that. So I'd like to give you another example, more realistic scenario from a retail company. You have, in this example, different organizational units, different parts of the process. Here you see you have some kind of customers. You have a module for order management, inventory management, supplier, warehouse, inventory management, freight forwarders, and customers. So you see some order is given to the company, and then the order is processed in the company, and after that the products which were ordered by the customers are delivered into the company, are delivered to the customers. And you see some very complex behavior happens inside these systems. At this level of granularity, you cannot see the details. So let me give you some examples for the details, some details. Here in the first step, the ordering customer is Ute. Ute submits a purchase order with 3 different line items, for example, a hat, a computer, or some pair of shoes. And then you have a purchase order. The purchase order is then disassembled in the order management system to put forward some reservation requests for different products. There are different reservation requests executed, and some copies of the orders are used for some management purposes, just for the organization. And the reservation requests are then forwarded in the inventory management. The inventory in the warehouse is reserved for this order to really be sure that Ute can get her order. And these are some details, and the other parts of the process looks really the same. I don't like to go in every detail now, but I'd just like to give you a rough overview how this more realistic large process model might look like. Again, you can identify here 5 different steps, A, B, C, D, E, and you can use composition calculus to compose this larger business process, which describes the behavior of a retail enterprise. And what is also very interesting, you might not be surprised now anymore, this process consists of 26 different steps. Each different step has a different character, and of course you can just write them up. And the complete process is a sequence of this 26 steps. It's very simple, but you have to use composition calculus to really write that up in that way. What is also very interesting and really necessary to deal with large process models are 3 challenges. Wolfgang already mentioned some of them. I'd like to give you some more examples for this, why is this really interesting and why our use of the composition calculus might tackle with these challenges. And the first one is the use of objects and data. In the example, if you have a more closer look at the first steps, you have items and data. Ute, the customer. The customer typically is not a part of the retailer. The customer is outside the complete system. And typically the customer is a real person or a company. And this is totally different as the data in the system, the purchase order. On the one hand side, you have some real objects, and on the other hand, you have data, and these different aspects can be distinguished. Little excursus on that topic. Why is it important to distinguish between data items or real-world objects and data? Do you have any ideas why this might be really necessary to distinguish?
Because real-world objects are manipulated by real tools?
Maybe. This might be one explanation. I have interesting examples of that.
Okay.
This is a fish head. I'm not able to classify it. And to be sure, the fish head is on the left bottom of it. This is an item of the real world. And sometimes fish heads are free, so they have no price. But sometimes fish heads have a price. In this example, this photo I found, the fish head costs €9. I find this really expensive for a fish head, but Wolfgang told me, no, the fish head is the best part of the fish. So it might be that if you just buy the really good fish heads and not just the fish heads as is, this is really important. The girl over there is just nodding. So the fish head is a real world item. The price is just data about some real world item. And this is really important to distinguish that. Why is this really important? Wolfgang can eat the fish head, but Wolfgang cannot eat the price of the fish head. It's a totally different understanding. And if you just do software modeling, you just do modeling the data, but you are not modeling the real world. And there are many, many examples in which it is really important to understand the environment of the software, so you really have to get an understanding of the real world items in your application. The second example, which is really important, is an interconnection between different cases. It's a common terminals in the workflow domain. You have some cases, and it always is a question how different cases might interrelate together. And as you see in this small example, there's a purchase order, which is typically one case. And in this example, you have 3 different reservation requests, and each reservation request belongs to one purchase order. It's one purchase order with 3 different line items, and for each line item there's a need to push forward the reservation requests. And you just see that this is very nicely modeled, that the composition calculus allows you to describe this relation without being very complicated mathematical terms. You just have the single step of a disassembled purchase order, and you propose them with the 3 different steps of the reservation request. And I'd like to mention a third aspect, the composition of systems. The different parts of the systems are layered in different colors. You have the customer system, the order management system in the middle, and the reservation system. And these 3 different systems can be very easily composed together in the description of this processes. So, as you might see, as this small example shows, that the composition calculus really helps you to describe 3 very important aspects of larger business processes. So, now I come to the last part of my talk, large process models. And before I go into this part, I'd like to make a small commercial break. And my colleague from the marketing department always says it's a good idea to repeat some commercial messages. So I just want to say that our book on understanding the digital world is almost out. I have a preprint here. If you really are eager to look at this preprint, just come to me after the session and you can have a deeper look on this. And I think Wolfgang will always exact some pre-orders for this book, so it's no problem. If you're interested in this, just came to me. But now to the idea of large process models. The idea of large process models is really simple. From the first point of departure, you have a large language model, and you use the large language model in the context of business process management. And this is my interpretation. What is the idea of large language models? But of course, if you're already familiar how large language models might be used in business process management, there are very different ideas how to use them. And from my understanding, there are 3 different approaches which can be used, how large language models can be used in the context of business process management. 1, 2, 3, fine-tuned large language models, large language model agents. In the morning, I talked to Harald Schöning and was telling what is a large language model. He says that it's a large action model from his perspective. So if you might never heard the term large language model agent, but the term large action model, I think they are quite similar. And a third example are the large language models I like to call native large language models for business process management. Let me come to the first type. Large language model is a fine-tuned large language model. There are different use cases out there, different evaluation and application scenarios. And I think the main idea is that you use the typical well-available large language model and try to fine-tune it in a particular domain of business process management. First example I'd like to show is a generation of a process model. And in this application domain, you take some input text and tell the large language model, please generate me a process model. At the beginning of last year, I wrote a first paper on that. Here's a task definition. It's a very simple description of the task. I don't want to read to you the complete details of this process description. Just want to give you the idea. It's a very simple task definition, and then you use some kind of large language model and tell the large language model, please generate me a process model for that. For example, in this application, we write, please tell me an Heraclid model, and we use some notation styles for the process definitions I give to you in the second part. And this is also the result of the model. It's not completely perfect, but you just see it's an idea how to use a large language model in the context of business process management. There's also the inverse idea, model explanation. And here the idea is that the input is the process model, and you tell the process model, the large language model, oh, please explain me this domain description. So it's the other way around. If some people are not used with the graphical description, they get some kind of natural description of the process. There are many more application cases out there. All these application cases work on the idea that they use a typical large language model, for example, ChatGPT, try to train, fine-tune it from an application domain perspective and from a modeling perspective. There are so many different techniques. You already might heard for one-shot tuning, fine-shot tuning, few-shot attempting, and things like that. I don't want to go into the details, but this is, of course, one idea how large language models can be used in this domain. I now come to a second application domain, a large process model as a large process model agent, or as Harald Schilling in the morning says to me, oh, this might be also a large action model. What is this? We have a large language model, and the large language model is just part of a bigger system, a large language model agent, and this kind of agent is not a human agent, it's a computer agent, a virtual agent. And this virtual agent has access to some kind of environment, some possibilities to observe the environment, and some possibilities to execute actions in the environment. And this is the idea of a large action model. Inside the large model, inside the large language model agent, there are so many different more components, a memory system, some kind of inference machine or things like that. I think this is currently a topic that is really evolving, but this is of course one idea. For this kind of usage, I have an example for you. It's an example from some colleague. It's a web shop example. Here you can see the instruction for the web shop agent. I'm looking for a small portable folding desk. It's the first step, which is told to the agent. Then the agent looks at the internet, browses the web shop. The web shop produces some results, some descriptions. Then the agent identifies the results, analyzes the results, identifies that there's particular this desk which the customer might be interested in, select the color of the different desk, then some details of the different items are looked inside, and if the agent really like to buy it, then the training mechanism gives him some reward for this. And, by doing this kind of training for the large action model, the agent uses a large language model to really buy an item from the web shop. There's also some technical stuff in the bottom. I don't want to go into the details. What is really interesting from my point of view, this is not just some abstract idea. There already exist some concrete benchmarks for some concrete application domains. Here's some results from such benchmarks. The example here in the bottom is very similar to the web shop example, but it's the buying of a ticket for a flight. Then we have some ticket system for this. Another example is a cooking example. Please put a pan on the dining table in a cooking simulator. And there are many more different application domains in this benchmark, and you see different environments from operating systems, database systems, different computer games, also natural thinking puzzles. And in all this, there exists concrete benchmarking results, how different language models really perform in these different application scenarios. And the best thing you can do is that you get 5 points, and you see ChatGPT-4 almost get not 5 but 4 points. The other different language models performs much worse in these different agents. So you can call this large process model agents or large action models. Now I come to this, what I call native large language models. And here the idea is that you have a large process model. You have on the left interface the event logs, some running processes, and then you try to predict the next process step. This is a typical example for this. But of course, you're not only interested in predicting the next process steps. There are typically many more features you might to predict in these contexts. For example, you might be interested in the remaining processing time of this particular process run. You might be interested in the time when the next event might happen. You might be interested in the outcome of the process. Or of course, you might identify some anomalies in the process which is currently running. For example, there may be some fraudulent behavior or some anomalous customer interaction, like credit cards or things like that. And this is, I think, the main idea of a native large process model. In the past, we already developed such things. There was a paper some years ago on decision support systems where we used very rudimentary deep learning techniques for doing some process predictions. Last year, we published a systematic literature review on this area, and I'm already a little bit proud of that because it's published in Artificial Intelligence Review, and I think this is really interesting from my perspective as a business informatics researcher, that from my point of view, this field of using deep learning techniques for process prediction might involve in the artificial intelligence domain. And also, some colleagues published a couple of weeks ago at Kaiser a process transformer network for doing some process type prediction. And just to show you from this publication that such process prediction framework really have some impact. In this example, you see in the left hand different process logs which were used for the training purposes. Then you have some dummy evaluation, and the dummy evaluation is more or less the median of the former process sizes, just an average of the process durations which are in event logs. And then there's a comparison with different architectures from different process architectures, and you see the PGTNet is very good in estimating the remaining time for this particular process. It's much better than just some naive prediction that might be done without some very primitive techniques. So from my point of view, it's a very interesting field of research for this. Now I'd like to come why these different application scenarios really work. And I think one reason for that is that there is a central theorem for really understanding what is a process. And the central idea of this theorem is that each single process can be composed from different process steps. So if you have a process R, which is composed from different process steps, then it is always possible to compose each process from the application domain from different steps. And the proof of this theorem is really simple. It's not a very difficult proof, not so complicated as Wolfgang told us for the composition, the associativity of the composition calculus. It's a really simple proof, but the idea that every process really can be composed from single process steps is a very simple, very simple idea, but it's really important to understand why it is possible that such large language models can predict the next process steps. So very, very interesting insight in that. And why it is particularly important. Each process step can now be interpreted as a token, as a vocabulary of the system, and if you have an idea of the different tokens, then you really have the tokens which can be used for the usage of large language models, and you can use the conventional methods for large language models compared to the other domains I showed you at the beginning of my talk. So now I come to my conclusions. From my perspective, and hopefully you all agree, large language models evolve into some kind of foundational technology in informatics. From my perspective, even in 5 years or 10 years, we still have these kind of foundational technologies for very, very different application domains. I showed you some examples how large process models can be used. Large language models can be fine-tuned to particular application scenarios in the domain of business process management. You can use some large language model agents or large action models. So the large action models do not produce text, but action descriptions or things like that. And I already showed you the idea of a native large process model in which the model is trained from scratch with different event logs, and these event logs are identified as the process steps in the business process management domain. And what is, from my perspective, really important, that the composition calculus provides you with a theoretical foundation for really large language. Thank you very much. And if you now have a small overload to Wolfgang, I will gladly answer.
Without paying Wolfgang, because it's your question. Your famous theorem on page 77. Each process model has logic that determines when or if a certain step has to be performed. How is this brought into, because Wolfgang only said that there's it's logicless composition.
I don't believe that, but I will look into the publication if you give me a link.
Say again?
I don't believe what you're saying, but I will look inside the publication if you give me a link.
I don't get the answer.
I didn't get it either.
You asked me that there was already a proof of a central theory.
No, the question was completely different. If you take a look at process modeling languages, they all include logics that govern the execution of a step, whether or not it should be executed.
Conditions and so on.
Yeah. So how is this folded into the black dot operator that you say that you compose a process model out of primitive steps?
I think I didn't get the question correctly.
Can you go one or two slides back? One more back, yeah.
So
The point is, if everything is conditional or unconditional, how do you get the conditions in this operator?
Thank you, Peter.
Now I get it. If you have a condition in the process, then you have two different runs. It's a different process run from a terminological perspective. So, for example, if Ute puts forward an purchase order, and then the decision is the inventory has the article which is ordered or does not have the article installed. Then you have two different processes.
He's talking about processes, not models. We are talking about process models.
Me too.
Yeah, but no, he's not talking about process models. He's talking about runs of process models.
It's the interfaces, I think. It's the interfaces that have the conditional aspects. Sometimes you have the output interface and sometimes you don't.
But where is the condition?
The condition is that in the software.
On this level, there is no condition.
Okay.
You have, on the one hand, the process order routers, and the article is not installed.
Okay.
Or you have the other process, order routers, and the article is installed. It's two different processes.
I think it's not the process as we know it, it's the different traces of the processes. In one sense.
Now you use the famous trace notion. I would not use the trace notion in this context.
More questions?
Thanks for the talk. Can we go to slide 72, please? Yeah. Regarding the event logs, I don't know if you have seen or do you think it's possible to directly plug there some raw data signals from sensors or IoT directly to the model to be able to understand that raw data.
If I understand your question correctly, you try to feed into more data into the large process model?
That in the event logs, there
Sure.
should be real, just raw data from any kind of sensor, IoT system. That could be possible.
I can imagine that it's possible that you feed more data into it. Sure.
That's really quite interesting. So you need to analyze that data that's directly plugged into the model and able to understand what is happening according to the sensors in the system.
This is just a rough picture of the possible approaches.
Okay.
So if we consider the ordering process, then you would have, in your terminology, one process. If you order one item, you have another process. If you order two items, etc. But wouldn't it then make more sense to call the set of your sub-modules to be the process, and it will automatically assemble itself according to the interfaces, depending on whether you order one item, two items, six items?
Of course, if you look at the complete hierarchic approach, then you see that there is above the level of simple process description another level where you will have some kinds of system models where you have some conditions as Frank already introduced. But on the level, as Eric introduced the idea of large process model, you just have the processes with different process types and approaches.
One process would be one instance of this.
If you use this terminology, yes.
Okay.
More questions?
To prepare myself for a discussion with you, can I express something equivalent like a BPMN process model with this approach?
You would like to
I hear you and Wolfgang saying, get rid of approaches like BPMN. Wolfgang has a provocative slide. This take your, my favorite modeling language is now BPMN. And Wolfgang said, I can toss it and use Heraclit. So it must be possible to express something like BPMN with Heraclit. Is that true? Or
I don't see any problem that you can phrase some ideas of BPMN, but if you look at BPMN, I think there are many concepts and also some empirical evaluations that just 20% of all BPMN concepts are really used, and I would say that Heraclit has particularly this 20% in a very good way and not in the bulky way from BPMN.
And it depends on which domain, which 20% are used. I know. I know. So,
but it's empirical evidence. If you look at empirical studies, then it's pretty clear which 20% are typically used.
we have enough to discuss for that.
Yeah, hopefully.
More questions? No, then we thank again our speakers. And we reconvene at, I think, 3 p.m., right? Okay, thank you.